This is the screencast for section 6.5, example 2, anti-differentiating with partial fractions. Okay, so you might look at this antiderivative and go, all right, can I use substitution? Well, no, it's not. Those two functions aren't really related by a derivative. Can I use integration by parts? Well, it's not really two functions being multiplied by each other. They're really being divided, which means the one of them is 1 over x squared minus 1. Maybe anti-differentiation by parts will work, but let's try anti-differentiating with partial fractions. Now you may notice the degree in the numerator is greater than the degree in the denominator. That doesn't work with partial fractions. We need it to be the other way around. We need the degree in the numerator to be less than the degree in the denominator. So we're going to use long division to help us write that out. I'm going to do long division x squared minus 1 on the numerator, 3x to the 4th plus 1. So of course I got those three terms of zeros. And I'm finding what can I multiply x squared by to get 3x to the 4th. I get 3x squared. I'm going to subtract that. We'll distribute the 3x squared to both terms in the divisor and then subtract them. And I get 3x squared, so now what can x squared be multiplied to get 3x squared? And then of course the plus 1, the new term that I need to drop down, and that's a plus 3. So again, I'll distribute that 3, subtract it from both the terms, and then I have a 4 as my remainder. So now I can rewrite the original integral of a rational function as the integral of 3x squared plus 3, the quotient, plus 4, the remainder, that remains to be divided by x squared minus 1. That works out much better for anti-differentiation with partial fractions because now the degree in the numerator is less than the degree in the denominator. Okay, so let's actually take the antiderivative of each piece at a time. So we have the antiderivative of 3x squared, which is x cubed, antiderivative of 3, which is 3x, and then this last part, 4 over x squared minus 1 dx. Well, again, you can't really use substitution, you can't really use integration by parts, so I'm going to now rewrite this as a partial fraction. So the denominator factored is x minus 1 times x plus 1, which means that there can be some constant over x minus 1 plus some constant over x plus 1 that will have the equivalent graph to this expression. And so now I'm going to set up my partial fractions as a times x plus 1 plus b times x minus 1, which would equal 4, the numerator from before I split it. If x equals negative 1, a would get multiplied by 0 and I solve for b, which would be negative 2. If x equals positive 1, b would get multiplied by 0, so a would equal 2, which means the antiderivative that I am trying to find can be rewritten as the antiderivative of 2 over x minus 1, the a value over x minus 1, dx, so I'm going to split up the integral here, plus another integral of negative 2 over x plus 1, or of course minus the antiderivative of 2 over x plus 1 dx. Now those antiderivatives I can take very easily. I have x cubed plus 3x left over from back here when I took the antiderivative of those two terms using the power rule. Now the antiderivative of 2 over x minus 1 is, I can bring out the 2 as a coefficient, and that's the natural log of the absolute value of x minus 1, and then minus 2 times the natural log of the absolute value of x plus 1, and of course, don't forget your plus c. So we used a lot of stuff in this problem. We used long division, we used anti-differentiation with a basic power rule, we used partial fractions, and then we used anti-differentiation of logs. What a mess, but sometimes you gotta do what you gotta do. The now try problem number 7 has the degree in the numerator larger than the degree in the denominator, so we're going to use partial fractions again, but first, yeah, we gotta dabble with long division. Here we go. So because the degree in the numerator is larger, we're going to rewrite this using long division. X squared times 2x will be 2x cubed, so I distribute that 2x and subtract, and I get 8x. Now that's it, only one step in my long division, which is really nice. So now I can rewrite the antiderivative as 2x plus the 8x that remains to be divided by x squared minus 4, and then of course with the dx. Now I split that integral because I can take the antiderivative of 2x plus 9, I can take the antiderivative of 2x dx. But now this part over here, I will get to use u substitution. This is a composition function where the denominator is related to the numerator by a derivative. So I'm going to use that u is going to be x squared minus 4. And then du is 2x dx. So that means dx is going to be du over 2x. So I'm going to substitute that in. First of all, the antiderivative of 2x dx is just x squared. Plus, and then 8x is now going to be over u. Dx is du over 2x. If I simplify inside that antiderivative, I have the antiderivative of 4u to the negative 1 du, which means that the antiderivative is 4 times the natural log of the absolute value of u plus c. So here, I could use 4 as an exponent of what's inside my log, which means I don't need the absolute value anymore because the absolute value is preventing any negatives from happening, but a fourth exponent would do the same thing. Plugging in x squared minus 4 for u, I get my final answer here. Now we could have done the same thing on the previous problem. If you didn't want to write the absolute value, each of these terms had 2 as an exponent of the expression you're taking the log of. So you could have just used 2 as an exponent and wrote it without the absolute value. Like that.